Hey, my name is Reagan. I go to Cal Poly San Luis Obispo, and today I'm going to be talking about Muon, Veto, and uniformity tests for CUORE and CUPID. Click on maybe whatever. So CUORE is an experiment, or one of many experiments, that's searching for neutrino-less double beta decay, and it's doing so in tellurium-130. So ordinary beta decay is when a neutron in a nucleus decays into a proton, an electron, and an antineutron. Here at the top, you can see double beta decay, which is when two ordinary beta decays occur in the same nucleus. And at the bottom, you can see neutrinoless double beta decay, which is when two beta decays occur, but there are no neutrinos. And so this is what CUORE is searching for. So why do we care about neutrinoless double beta decay? Well, one, it would help us explain the matter-antimatter asymmetry. This is the fact that we assume equal amounts of matter and antimatter were produced during the Big Bang, but we observe a lot more matter now. And so neutrinoless double beta decay would be a small lepton number violation that could help explain this. It would also mean that the neutrino is its own antiparticle, or a Majorana fermion. We currently treat neutrinos as Dirac fermions, or particles that are distinct from their antiparticle. And here at the bottom, you can see pictures of Majorana and Dirac. And this discovery of this decay would also have implications for understanding neutrino mass. And so the CUORE detector is 988 cryogenic calorimeters. You can see here are the CUORE towers. The crystals are made of tellurium dioxide, and they're kept around 10 millikelvin using a cryostat. And that's because the detectors work by measuring the temperature changes when an event happens in the crystal. And so CUPID is CUORE's upgrade. It aims to use heat and light and coincidence in order to discriminate against background events. And the goal here is to lower the background in comparison to CUORE. And so here you can see the CUORE detector, or the crystal calorimeter, or calorimeter, and you can see there's a thermistor that measures the temperature change when an event occurs in the crystal. With CUPID, there's a thermal sensor that measures the temperature change, and there's also a light detector that measures the amount of light produced when the event happens. And because we know that the amount of light that's produced in alpha events is going to be different or less than the amount of light that's produced in beta or gamma events, we'll be able to identify which events correspond to alpha and be able to cut them out of our data. And so one problem with CUPID now is muons, which are particles that are created when cosmic rays interact in our atmosphere. They create showers of other particles, and sometimes those particles are muons. And so CUORE is actually located under this mountain, and that's for shielding, but muons can still get through the mountain. And so instead of stopping muons, we need some way to tag them in our data. The problem is we can't use light and heat signatures in order to ID them. And they could deposit energy near our region of interest, or where we expect neutrinoless double beta decay to be. And so our solution is a Muon Veto system. Right here is a picture of how the Muon Veto panels would be arranged around our detector. And so the Muon Veto panels are a plastic scintillator that has embedded wavelength shifting fibers that when a muon goes through, will scintillate so that the fibers will collect the photons, and then they'll be sent to the SIPM, silicon photomultiplier, which acts as a light detector. In the bottom corner, you can see one of these panels in a dark box where it's been wrapped, and it's wrapped in Tyvek reflecting paper, aluminum foil, and black tape. And that's because we want to keep the scintillating light in, because that's what we want to measure, and we don't want any background light. And so what Yale has been doing is performing uniformity tests, or light uniformity tests, on this 100 by 50 centimeter panel using a 25 by 25 centimeter panel to test different locations. But what hasn't been confirmed until now is whether or not the small panel itself is uniform. And I just want to point out that the swirly design on the actual panel is meant to improve uniformity. And so how are we going to test this? We're going to measure the light yield at different locations on the small panel, where the light yield is the amount of light that the panel detects per unit energy deposited in the panel. And ideally, we want it to be uniform throughout the panel. And so here's the equation we used. We'll need to find M, which is ADC per mega electron volt. Here, ADC is analog to digital converter. It's the signal that our DAC, or data acquisition system, outputs to us. Because our DAC doesn't know about energies, it knows about voltages. We'll need to find P, which is ADC per photoelectron. And then we'll need to find the gain ratio, which is the ratios between a high and low gain. And so to take data, we placed a small panel or a smaller panel on top of our small panel, and we got our data in ADC counts. And so at the top, you can see our high gain data, and you can see there's photoelectron peaks in that spectrum. And we want to find ADC per photoelectron. So what we did was we fit the data, and we found the distance between the peaks. On the bottom, that's our low gain spectrum. We want to find ADC for MEV, and we know that the peak falls about at 5 mega electron volts, so we're able to use that bit to determine the ADC per mega electron volt. And then lastly, we plot the transfer function in order to find the gain ratio, and that's that third plot there. And so we had two methods of taking data. The brick, which is a 6 by 25 centimeter panel, and we used this to test 4 different locations on our small panel. And this method was successful to determine uniformity. We also had a tiny panel, which was 6 by 6 centimeters, and we used this to test 16 different locations on our small panel. And we didn't determine uniformity this way, but we did have an interesting lump in our data. And so with the brick, we used an OR trigger, which means it will take data in both panels if there's an event in either panel. With the tiny panel, we used a coincidence trigger, which means it takes data in both panels if there's an event in both panels, but it doesn't take data if there's only an event in one. And with the brick, we had to go back and actually add a coincidence trigger in our analysis. And that's just to test specific locations. And so here are our results. On the x-axis, that's locations on the small panel. So I had a map that was 1, 2, 3, 4. And then on the y-axis, that's light yield. And you can see the values are, or the values fall within each other's error bars. So we consider this panel uniform. And so what's really interesting is we found this lump when we ran our tiny panel in coincidence with our small panel. And the reason this lump or this extra peak was so weird to us was we expect to see a peak that corresponds to background events, that's kind of here, and a peak that corresponds to muons, which is here, but we don't expect to see another peak. And so we were kind of confused what was going on. And we spent a lot of our summer trying to figure out the cause of this lump, but I'll give you the fast version. We used a digitizer in order to see the waveforms of our events. And the whole purpose of this was we thought maybe we were capturing some kind of unknown noise, and that was what was causing this lump. And so you can see here, we were running our panels at 55 volts. This is what our waveforms looked like. And 55 volts was the voltage used when the uniformity tests were being done on the 100 by 50 centimeter panel. And we tried turning down the voltage to 53 volts, and you can see a lot of the distortion and saturation has kind of gone away. There's still some weird looking signals, but it's decreased a lot. And you can see at the top, this is kind of what a good pulse would look like. And so, final thoughts, we turned down the voltage and we saw the counts in the lump go away. You can see this is actually on our spectrum. As we turn down the voltage, the lump decreases. And one thing that we also noticed was when we ran the brick, for instance, with the small panel, there was also a lump there, but the lump was smaller. And the brick is larger than the tiny panel. So we think that it has to do with the size of the size of the brick. And so, yeah, we found that the higher voltage distorted the waveforms in the smaller panel. And so in conclusion, we confirmed the uniformity of the small Muon Veto panel, that are used to run that is used to run uniformity tests on the larger panel. And we found the source of the lump in our data. And we found that we need to choose the voltage bias based on the size of our panel. Lastly, a couple other things I learned this summer. I was clean room trained because Yale is interested in fabricating line detectors here on campus. So that's a picture of me at the clean room. And I also learned how to solder in order to use the digitizer. Thank you.
Any questions?
That's one about this lump. So, you know if the saturation is what you expect from your ADC, or you're getting like after pulsing maybe in the SIPO? So if you're getting lots and lots of light on them, you know what? Because it has quite a funny shape that it hangs around for.
Yeah, I'm actually not sure why the shape is doing that.
Yeah, I think it's mainly from ADC. I don't think we observe after pulsing.
On your uniformity measurements, do you think this impacted those, or is that completely different?
Can you repeat that?
On the uniformity measurements, did the saturation affect your conclusions there in any way, do you think?
So we never actually looked at the waveforms because we used an OR trigger. We were only seeing the lump with the coincidence trigger.
Oh, I see that.
Any questions?